Hello everyone, welcome to CS188 section 9. Today we are going to talk about the hidden Markov model and particle filtering. So in this video, I'm going to do a brief overview for both the concepts, and then I'm going to go over the first two questions on this worksheet. So without further ado, let's jump right into it. Number 1. Hidden Markov models. So there are two types of variables in this in the hidden Markov model. The first thing is the hidden variable, in this case denoted as the WTs. And then we have the evidence or observation variables denoted with OT. So there are a few probability tables that we consider as the building ground for the hidden Markov model. The first probability table will be the transitional model of P WT plus 1 given WT. So as you can see from the format, it gives the probability of the next hidden state given the current hidden state. So in this figure over here, this transitional model P is denoted by this horizontal edge connecting W1 to W2. And then the next building block will be the sensor model, which is the probability table of P O sub t given W sub t. So from the format, we can probably conclude that this is a probability table of the observation at a particular time step given the hidden state at the time step. So in this figure over here, this probability table is given by these two vertical edges. So the last building block that most of us usually overlook is the distribution for the initial distribution for the hidden state. In this case, that will be P W sub 1. And the reason this is different from the two tables up here is that it's not conditional on anything. So think about it as like the start of the world, right? Then you're not conditioning that on anything. So there are a few relationships between these three tables during which, so if we combine these three tables in a particular way, we will be able to get the joint probability over all the hidden state from time 1 to time t, and all the observations from time 1 to time t. But without going into the specific, let's introduce some belief distributions. So I personally think of these belief distributions as intermediate blocks. So basically, it will take some intermediate values that we compute up to some time step, and then adding one new table at a time to build up to the final product that we're interested in. So the first belief distribution table is just a regular B W sub t. So this is the equivalent to the probability of the hidden state at time t given all the observations from time 1 to time t. Okay. So this is equivalent to the distribution for the current hidden state at time t, given all the observations from time 1 to time t. So one way to think about it is like if I have all the evidence, what would the distribution for the hidden state at the time step t look like? The other distribution is the B prime W sub t. And this is the probability table for the hidden state at time t, given all the observations from the start all the way to time step t minus 1. And this is fairly important because this belief, B prime, is more of a guess than just a regular B W sub t, because it's not conditioned on the current observation. It's conditioned on all the observation up to but not including the current observation. So I hope that clear up the syntax for all the building blocks as underlined over here, as well as the 2 intermediate block highlighted over here. Now let's talk about the forward algorithm. So there are 2 steps in the forward algorithm. The first one is the prediction update, where we compute B prime of the next hidden state, WT plus 1. And this is the formula. So we basically we will have the belief distribution of the current hidden state, WT, and all the transition model over here. But now we want to know what will be the guess for the hidden state in the next time step. So this formula can be kind of visualized in the following way. So let's say that you have so let's say that you have 3 possible values for both WT and WT plus 1. So essentially, you have compute everything up to time t. So you have the BWT figured out for all these 3 possible values for the hidden state WT. But now you're going to take the crossover to the next time step, and that is with the transitional model, right? So then basically now if I want to query the belief distribution for A at time step t plus 1, I'm going to take the B of A over here at time step t, but we are taking the transition probability here as the bridge to cross over. Then we'll sum over all the possible values for the hidden state at the current step, and then that's how we get B prime for the hidden state at time step t plus 1. Once we have that, we're going to perform something like called the observation update. So the observation update basically incorporate the evidence into the probability, into the belief distribution. So the observation update basically incorporate the observation into the distribution. So the observation update basically incorporate observation into the belief distribution by multiplying the belief without the observation at the t+1 stage with the probability of that observation given that a particular hidden state at t+1. And just a quick thing to watch out over here, that in the observation update, the belief distribution doesn't come out to equal the product of these two, and it's just a proportional sign. And the reason for this can be found in the lectures, so make sure you understand how it works. But this is a proportional sign instead of a equal. So let's see how the concept is reflected in this particular problem. We have the same figure as above, and we have the three building blocks of HMM, which is the initial distribution, the transition model, and the observation model. Here the hidden state W's can take on values 0s and 1s, and the observation can take on value A and B. So part 8 of this problem asks for the joint probability of W1 and O1 equals to A. So basically it's asking the joint distribution for both 0 and 1 values of W1. So let's take a look at what would constitute the joint distribution of W1 equals to 0 and O1 equals to A. So by chain rule, we know that this is equal to the probability of W1 equals to 0 times the probability of O1 equals to A given W1 is equal to 0. Now we can plug in the values that, okay, so the PW1 equals to 0 is 0.3, and the probability of O1 equals to A given W1 equals to 0 will be 0.9. So we have these two numbers, and we multiply them together to get 0.27. That's going to be PW1 equals to 0 and O1 equals to A. Now let's take a look at what's going to happen with PW1 equals to 1 and O1 equals to A. So we apply the same logic. The first term in the multiplication will be the probability of W1 equals to 1. In this case, that will be 0.7. And the second term in the multiplication will be the probability for the observation equals to A, conditioned on the hidden state being 1. So that's going to be 0.5. So that's going to be 0.35 for the case of W1 equals to 1. Now, with these two values in mind, let's take a look at how we can solve part B. So part B is asking, using the previous calculation, compute the probability of W2 and O1 equals to A. So here again, W2 can take on both value 0 and 1. And one thing we can notice is that the observation is only up to time step 1 when the hidden state is already at time step 2. So if we recall the prediction update on the top, this is exactly equivalent to B prime of WT. It's because we can see the last observation we see is the T minus 1. And we want to know something about WT. So the way we compute P prime of WT is using the prediction update, where we sum over all the possible previous hidden state that can lead us to that particular hidden state at, in this case, time step 2. So we can look at it in this case of, I'm just going to write the part B on top here because it has a little bit more space. So let's take an example of P W2 equals to 0 and O1 equals to 8. W2 can be both 0 and 1, but in this case, we're just looking at 0. So that is going to be the summation over all possible values of W1. And the transition probability from W1 equals to W1 and W2 equals to 0 times the belief, the true belief for W1 equals to that particular value of W1. And this term is exactly the result we got from part A. Because if you look at the notation up here, the true belief B of WT is the probability of WT given all the observation up to the point time t, up to the time t. So if we expand the terms, it's going to be, since W1 can take on value 0, either 0 or 1, so when W1 is 0, the first term is going to be W2 is 0 given W1 is 0 times the belief that W1 is 0. And the second term is going to be probability of W2 is 0 given W1 is 1 times the belief that W1 is equal to 1. So the transition probability from 0 to 0 is going to be 0.4. And the true belief of W1 equals to 0 can be drawn from part A. That's going to be 0.27. And in the second term, the transitional probability from 1 to 0 is going to be 0.8. So we have 0.8 times the true belief, which is going to be 0.35 for W1 equals to 1. And if we plug that into a calculator, we will get 0.388 for W2 equals to 0 and observation 1 equals to A. So if we use the same method on value W1, W2, if we use the same method on W2 equals to 1, we'll get that probability is going to come out to be 0.6 times 0.27 plus 0.2 times 0.35, and that's going to give us 0.232 for W2 equals to 1. Condition and for W2 equals to 1 and O1 equals to A. So that's the first two parts of the hidden Markov model problem, where we first calculate the true belief B. So in part A, we basically calculate the true belief B W1, and in part B, we calculated B prime of W2. Now let's look at part C. So using the previous calculation, compute W2, the probability of W2, and O1 is A and O2 is B. Here, we can basically see that this is calculating the true belief of BW2. So what we can do is to, in the case of W2 equals to 0, this is going to be the same as the probability of O2 equals to B given W2 is 0 times B prime of W2 equals to 0. So the first term can be directly inferred from the table. So O2 is B and W2 is 0. That's this row. So we get value 0.1. And the B prime of W2 equals to 0 is basically what we calculated in part B, and this can be found over here. So that's going to be 0.388. So the final answer for the case of W2 equals to 0 is going to be 0.0388. And with the same calculation, we can find that P of W2 equals to 1, O1 equals to A, and O2 equals to B. That's going to come out to be 0.116. I'm going to omit the intermediate step, but it's exactly the same pattern matching. So you basically use probability of O2 equals to B conditioned on W2 equal to 1 times the B prime of W2 equals to 1. So yeah, that's the big idea over here. So now we have all the parts from A to C. We want to compute a normalized version of the true belief B of W2. Normalized. The reason I say normalized is that this is trying to find a probability condition on the variables. That's when you know the probability according to all the values of W2 must add up to 1 in this probability table. So what we can do is simply perform a normalization trick. So P of W2 equals to 0, condition on O1 is A and O2 is B, will just be the actual value, which is 0.388, divided by the sum of the two values. And this is going to come out around 0.25. And for W2 is equal to 1, it's the same idea, but you just put 0.116 on top instead of 0.0388 on top, and that's going to come out around 0.75. Okay. So I hope this walkthrough of the problem is helpful. And now we're going to take a look at the other concept in this worksheet, which is going to be particle filtering. So now let's talk about the concept of particle filtering. This method is an approximation used to answer queries in the hidden Markov model. The reason this works to some extent is because when the number of particles is big enough, it's able to quantitatively approximate both the prediction and observation update in a regular hidden Markov model. So the prediction update is approximated by the transition of each individual particles, and the observation update is reflected by weighing the particle according to how much it corresponds to the observation and changing the distribution that will sample the particles in the next time step. So let's look at this concept in action in this particular problem from the worksheet. So as we can see, this is the exact same setup as the previous problem. The only thing changed is that now we're starting with two particles representing our distribution for the initial state. And one of them is in state 0, and one of them is in state 1. So now we have an array of random numbers between 0s and 1, which we use to approximate randomness in our action. So in part A, we're going to compute the weight of these two particles after we observe the evidence O1 is equal to A. So that means we assume both particles are valid, but they just hold different weight according to our observation. So let's take a look at particle 1. So the weight of particle 1 after we observe A is going to be the probability of O1 equals to A conditioned on W1 equals to 0. And that's going to be 0.9. And the same way for particle 2, where the W1 is 1, that's the weight is going to be the same as probability of observation being A conditioned on W1 equals to 1. And that is going to be 0.5. Okay. Now, in part B, we're going to perform a resample based on the weight we just calculated. Notice that the weight of particle 1 and particle 2 does not add up to 1. That means we must normalize the probability distribution before we resample. So if we normalize 0.9, 0.5, we're going to get 0.643 and 0.357. So that basically means if the random number is between 0 and 0.643, the new particle will be in the same bin as particle 1. Which is 0. And if the particle lands anywhere else, that will correspond to particle 2. So now we use two random numbers to generate the two new particles. The first random number we draw is 0.22, and that falls in this interval. So then the resampled P1 is going to be in bin 0. And now we sample again, but 0.05 is again in the bin 0 to 0.643. So P2 also goes to 0. Now we're going to approximate the prediction update by applying the transition model to both these particles. So since particle 1 is in hidden state 0, we're going to look at this part of the transition model. And any numbers between 0 and 0.4 means that the next state is going to be 0. And from 0.4 to 1 means that the next state is going to be 1. Now we take the random number, that's 0.33. It falls in this bin. So now particle 1 goes from 0 to 0. And particle 2, since the particle 2 is also at hidden state 0, it used the same part of the transition model, and we draw another random number, in this case 0.20. That still falls in this bin, which means the next state is still going to be 0. So after part C, we realize both of the particles land into state 0. And now in part D, we're going to compute the weight of these two particles after the evidence that O2 is equal to B. So since we are at hidden state 0, and the observation is B, the weight for both the particles are going to be 0.1, just reading straight from the table. And in part E, if we normalize the distribution, it's going to be 0.5 and 0.5 split between the two particles. But since both P1 and P2 are in hidden state 0 at this point, the resampled particles are still going to be in the state, because the probability of resampling to get 0 is going to be 0.5 plus 0.5, and the probability of resampling and get 1 is going to be 0 because there's no particle after the transition that's in hidden state 1. That means if you resample the particles, there's no way that any of them land in state 1. So regardless, we're still going to use up 2 random numbers from the list, but it's always good to keep track of that. So now in part F, we ask what is our estimated distribution for hidden states of 2 condition on that the O1 is A and O2 is B. Oh, by the way, sorry about the confusion in notation here, because this should be the weight of particle 1, and this is the weight of particle 2. So now we can see that both particles, after observation, update, resampling, and prediction update, end up both at hidden state W2 is equal to 0. Both of them are a hidden state W2 equal to 0. That basically means for the probability of W2 equal to 0 given observation O1 is A and O2 is B, is going to be 2 over 2, and that's going to be 1 because both of them are in W2 after getting these observations and obviously prediction updates, and the probability of W2 equal to 1 given these observations is going to be 0 over 2, and that's going to give you 0. So I hope this video is helpful in helping you understand the hidden Markov model and particle filtering a little bit more. If you have any questions, please feel free to post on Piazza or come to our office hours. Thank you. Have a nice day.